In this video, we'll discuss analog to digital conversion and how to do so with the PIC16F887. Analog to digital conversion is a very important process that will allow us to interface with a variety of external devices. So, why should we care? Well, in the real world, a lot of signals are analog. You can think about sound. So, even though we've seen some digital sound, we know that sound is of an analog quantity. So if we wanted to sample someone singing or an instrument or just someone speaking, there are a lot of analog characteristics to the signals that are involved in sound. And so using a microphone allows us to capture that sound and convert it into a digital format. A lot of sensors are analog. So you can think about things that measure temperature, because temperature is an analog quantity. You can think about things that measure position. Position is analog. You don't have to be exactly in this spot or that spot. You could be somewhere in between. There are a lot of dials that we may have. Think about volume knobs or things along those lines that allow us to turn things up or down. And the problem with having to interface with what is largely an analog world is that our computers, our microcontrollers that we're using, are natively digital, and so they need some way to take that analog quantity and convert it into a format that they are capable of processing. Converting from analog to digital is a process. It takes a representation from the real world and converts it into something that the human can understand. In large case, it may involve the use of a sensor, so some kind of sensor has to convert the real world quantity, our measure and, if you will, into some kind of an electrical signal, which may be analog, and then that analog electrical signal has to be converted on into the digital representation. And so what we're going to do is, over time, we're going to collect various samples of what that analog signal looks like, and if we piece together those samples with respect to time, we can get a better idea of what's happening with our signal. So here's an example here. This thick black line that you see represents an analog signal, and if we were to capture that at different moments in time, let's say each of these points is a moment in time where we're taking a digital snapshot, then we could say, well, at this time it was here, at this time it was there, at this time it was there, and then we could start to see a digital representation which looks somewhat like our signal. Of course, it's still very jagged. And the way that we can improve what our representation looks like is through two methods. One, we can sample faster, and that's going to get more accuracy from our representation along the horizontal time axis. And then we can add more bits, which allow us a little bit more granularity in terms of representing individual voltage levels in our vertical axis, our voltage axis here. So, what does an analog to digital converter do? First of all, we have to establish a voltage range, and then it's going to come up with a binary representation for where a particular analog signal falls between that minimum and that maximum voltage. We have certain numbers of bits available. Some cheaper analog to digital converters have fewer bits, some higher end ones have more bits, and that just gets into how sensitive that particular converter can be to small changes in voltage. So the number of bits available determines how good our representation can be with our analog to digital converter. So here's a very simple example. This is just a simple 3-bit analog to digital converter. In most cases you're going to have many more bits than that. It's not uncommon to have 8, even upwards of 16 bits in some cases to represent your analog data in a digital format. But just to convey how things work, you may have seen this in a previous course that you took in digital electronics, but if you don't remember that or you haven't seen it lately, let me remind you that in this example we have a signal on the range 0 to 10 volts. And so what we're doing with these 3 bits is we can actually divide voltage into 8 different voltage bins. And so if you happen to be in the lower 8th, that is between 0 and 1.25 volts, then your representation will be 0, 0, 0. If you happen to be in the next 8th, somewhere between 1.25 and 2.5, you'll be at 0, 0, 1, all the way on up to the highest eighth, that is somewhere between 8.75 and 10 volts, then you'll be at 111. You can think about the most significant bit as effectively determining whether you're in a higher voltage or a lower voltage situation. So if you are greater than halfway, that is greater than this 5.0 right here, then your most significant bit is set. If you go on and you split into two halves there, then you can once again subdivide, and amongst that upper half, if you have a 1, then you are in the upper eighth here, upper quarter rather, the top eighth and the next eighth. If you have a 0 there, then you're in the next quarter, and that puts you somewhere here. And then if you were previously in a 0, you know you're in the lower half, and this determines whether you're in the upper quarter or the lower quarter of that half. And each bit gets you to divide down into another half as you keep going further and further. So it gives you twice as much resolution to add one single bit. So if you have n bits, then you would have 2 to the n possible levels that can be used. In this case, we only have 3 bits, so our voltage range is rather broad. You can, in this particular example, can only narrow down your signal to anywhere within 1.25 volts. If you added another bit, then you could narrow it down to half as much voltage there, or 0.625 volts in that particular case. And the more bits you add, the closer you can get to exactly what voltage level you have coming in. So how is this done? Well, one way is to do what's called successive approximation. We talked about this in digital electronics last semester if you took that class with me. But the idea is that we're going to work one bit at a time. We're going to start with the most significant bit and determine if that needs to be a 1 or a 0 based upon the analog voltage coming in. And so if that analog voltage coming in is greater than half of our overall range, or that maximum full-scale voltage, then we're going to put a 1 in our most significant bit. If it happens to be less than that, then we're going to put a 0 in our most significant bit. If we did put a 1, we're going to go ahead and take off what that 1 represents, which in this case would be half of whatever our maximum voltage is, and then check the next bit to see if within our remainder we have 1/4 of the full scale of voltage, and then we would put a 1 or a 0 there. So this graphic illustrates that. If you happen to have an analog input signal that's represented by this dashed line here, and we look at where it is, it happens to be less than half of the full scale. So here's full scale voltage, here's 0. It's less than half of full scale, so since we're lower there, we're going to put a 0 here. Then we're going to move on to the next bit. Since we didn't put anything in, we're not going to subtract anything off. And then the question is our analog input greater than 1/4 of full scale? And as we see, it in fact is. So we put a 1 right there in our next bit. And then we move on, and we realize that this bit represents 1/8 of full scale, but we already represented 1/4 of full scale here. So the question here is, are we actually at a voltage level that is bigger than 1/4 plus 1/8 of full scale? And the answer is yes, we are. That's what this thick line represents here. So we put another 1, and so now we've got a 1 and a 1. We've represented 3/8 of our full scale voltage, and then we look to see if we would have within the next value, that would be 1/4 plus 1/8 plus 1/16, and we are in fact lower than that, so we would put a 0 right down there. So now that we understand the basic fundamentals of analog to digital conversion, let's talk about how to perform analog to digital conversion on the PIC microcontroller. So we have on the PIC 14 different input channels. We can perform analog to digital on none of them at all, which is what we've done up to this point. We've been in all digital mode. You can perform analog to digital on just one of them, or you can use all 14 of the input channels. But you can only do one at a time. So you would collect from one channel, then store it, collect from the next channel, then store it. And we're going to do that as we go through in some of our labs this semester. We're going to use other channels to store our representation, or to perform analog to digital conversion on multiple inputs. And so here we have a digital representation. The 16F887 has a 10-bit analog to digital conversion module on it. And because it's 10 bits, and we are in an 8-bit microcontroller, that's going to require more than one register to hold it. So the bits that are collected from the analog to digital conversion process are stored in ADRESL and ADRESH. So that's the analog to digital result lower byte and analog to digital result higher byte. And there's actually two different ways that that data can be stored in there. We'll talk about that in a later slide. But just know that those are the two bits, or two registers, where those analog to digital conversion bits are stored. The reference voltage can either be your +5 and your ground that power the board, or you have some other pins on the microcontroller that can actually be used to provide your own analog to digital reference voltage. So here are the pins that are utilized in the analog to digital conversion module. So anything that has an AN0, we talked about this early on in one of our first lectures. So AN0 is analog channel 0, AN1 is analog channel 1. Here is an interesting thing. This can actually be either your reference voltage, Vref minus, and this one being Vref plus if you wanted to determine your own analog to digital reference, or this can be another channel of analog 2 and analog 3. The choice is up to you. So you can use this particular pin in a variety of different ways. It can be RA2, it can be analog 2, and it can be your voltage reference for your analog to digital conversion. Here you see RA5, and that happens to be the same as analog 4. That's one where it skips. It's a little bit confusing. And then notice analog 5, 6, and 7 are actually on port E. And then over here on port B we have analog 8, 9, 10, 11, 12, and 13 for a total of up to 14 analog channels. There are quite a few registers involved in the analog to digital conversion process. We're going to talk about most all of those in the next few slides. The analog to digital conversion registers 0 and 1 determine the properties of our particular analog to digital conversion and then tell the PIC to go ahead and perform the analog to digital conversion. ANSEL and ANSELH we've been using at this point to make sure that all of our ports were in all digital mode. We're going to use those to determine which ones we want in analog mode. As we already talked about, the results of the analog to digital conversion come in here in ADRESH and ADRESL. The INTCON we've already talked about in a variety of other contexts in terms of external interrupts and timers. But now you'll also notice that one of the peripheral interrupts we have is for analog to digital conversion. So you can actually enable that in peripheral input enable register 1, and then the flag is in PIR1 over here. So if you wanted to use that, of course you have to set the GIE, you have to use a peripheral interrupt enable, and then you have these bits here for the interrupt enable and the flag. And then the different ports happen to correspond to where the analog inputs are coming in. Ports A, B, and E. Obviously, if you're using them in analog mode, you cannot use them in digital mode. And then TRIS A, B, and E are used and must be configured as inputs for any of the analog channels that you're using. So let's go ahead and drill down a little bit deeper in that. ANSEL and ANSELH we've already talked about quite a bit, and so these bits show you, depending upon which analog channel you want to use, if you want to use any of them, just go ahead and put a 1 in those particular channels. So if you wanted to use analog, if you wanted to use analog channel 0, you'd just go ahead and put a 1 right here. If you wanted to use analog channel 7, go ahead and put a 1 right there. And then for the higher ones that happen to be over in port B, or the same pins as port B, then you would do this. And then you just don't do anything with the upper 2 bits because we only have 14 analog channels. ADCON 0 is perhaps the most important register when it comes to analog to digital conversion on this particular PIC, because it does so much to configure exactly what channel you're doing your analog to digital conversion on and how fast you can do it. So you can actually set the rate of your analog to digital conversion clock based on the frequency of the oscillator. You can also do a dedicated internal oscillator, which is a little bit slower. But there's some trade-offs here. So if your goal is to sample as fast as possible, then you'd want to put 0, 0 and then just have it operate at half of the oscillation frequency of your crystal oscillator. But if you're sampling something that doesn't need to be sampled very often, and you only want to do it every once in a while, you might slow it down a little bit and have a little bit slower sampling clock. That's not going to give you the best resolution in terms of your time axis, but it can potentially save you on some energy. So if you're developing something that will be battery driven and you don't really want to sample very often, then you can slow down your sampling clock and just sample at a little bit slower frequency, and that will save you some energy usage on your battery if you're interested in power. But for this particular application, we're just running off of your laptop's power, and so you can plug that into a wall whenever you want. So we're just going to run it for the most part as quickly as possible at the frequency of the oscillator divided by 2. So we'll generally put 0, 0 in this class. Then in terms of which channel you want to select, so you can enable, using ANSEL and ANSELH, more than one analog channel. And so the next 4 bits determine which analog channel you're actually using. So if you put 0, 0, 0, 0, that's analog 0, all the way up through 1, 1, 0, 1 is analog 13. And so we generally will not be using these upper 2 values, so you don't have to worry too much about those. I think that's just to check to make sure your analog to digital conversion is working. I've actually never used those. And then bit 1 is the bit that tells you a couple things. If you're ready to start the analog to digital conversion process, you set that bit to 1. That's the go bit, and then it stays high until the analog to digital conversion is finished. And so if you want to do data polling, you can just do a little while loop that waits for that bit to go low. Otherwise, you can configure the interrupt, and then the interrupt can wait in the background while you do some other things. And then the AD on bit must be set, because that enables the whole analog to digital converter module. So if you don't put that bit on, it's kind of like the GIE bit in the interrupt configuration register. If you don't put that on, analog to digital conversion will be turned off. ADCON 1 is also quite important. ADCON 1 bit 7 determines how the data is organized in the 2 different result registers. So if you put in a 1, it is write justified, and we'll illustrate that in a later slide in just a moment. But what that means is the least significant bit of your result is going to be the least significant bit in the lower byte, and then it will go on up until you have the most significant 2 bits in the upper byte. Otherwise, if you do it as left justified, then the most significant bit in the upper byte will hold the most significant bit of your result, and then the least significant 2 bits will be down in the lower byte. It's really up to you, and it depends on your application as to which way you would want that data to be represented. Bit 6 does nothing here. Bits 4 and 5 determine what your reference is. So if you want to reference VSS and VDD as your positive and negative voltage range, which we will do in this class, then you just put zeros there. Otherwise, you can independently choose to use reference voltages at the reference minus and reference plus. And then bits 3 through 0 are not used. You can just ignore them. So this illustrates how those results can come in. So if you do a left justified, then that is like what you see down here on the right, to where your most significant bit is going to be here, your most significant 8 bits are going to be in ADRESH, and then your least significant 2 bits are going to be in ADRESL. If you do right justified, then you'll have zeros over here in the top 6 bits of ADRESH, and then your 10 bits of data will be located here. And so that's all based on your ADFM bit, which is in, as we mentioned before, your ADCON, I'm sorry, not your ADCON 0, your ADCON 1, bit 7. Alright, so also just a reminder, you need to make sure that your TRIS register bits are set for whichever analog channels you're using as input, and so that'll help you to configure the appropriate ports. You can look here at the pin diagram to remember which particular ports those correspond to. So if you're looking at the left side of the PIC, that may be in port A or port E, depending upon which channel you're using. If you're on the right side of the PIC, that will be in port B, so you need to use TRISB for these ones, TRISA for these ones, and TRISE for these three down here. If you're using the interrupts, then what you would do is you would obviously set the GIE bit just like any other interrupt. The analog to digital interrupt is a peripheral interrupt, so you would need to put a 1 in your PIE bit, and then you would also need to put a 1 in your ADIE to enable that particular interrupt. And then when it does interrupt, that will interrupt when the analog to digital converter is finished. Then you could, in your interrupt service routine, make sure you clear the ADIF flag, which indicates that analog to digital is finished. Obviously, if you're using any other interrupts, just like we've done in previous labs, you'll need to check which particular flag is set, just to make sure it is the analog to digital and not one of the other interrupts that you may be using. So here are the basic steps to configure analog to digital conversion. First of all, you want to go ahead and configure your ports. Configure them using ANSEL and ANSELH and also the TRIS registers so that they are inputs as appropriate, and they also are configured for analog or digital depending upon what mode you may be operating in. Then you want to use ADCON1, and that's going to set up your result as either left or right justified, and then you're going to determine whether you're using your +5 and ground or any other reference voltages that you may have. Then you want to do several things in ADCON0. You want to set up how fast you're sampling. In this case, we're generally going to do it at half the frequency of the oscillator clock. You want to turn on the analog to digital module. Then you also want to choose the analog to digital channel that you're going to be pulling data from. Notice that I left off setting the go bit. You don't want to do that in the first write because you don't want to say go and turn on the module at the same time. You want to set it up, determine which channel it's going to be on, make sure it's all powered on, and then the next thing you're going to do is set that go bit. Okay, so that's going to be after you've set up everything and told it how to orient the data and told it how to, in terms of which channel you want it to convert, all those types of things. Then you can either pull the ADCON0 go bit, go and done, tell you when it's finished, or you can configure your interrupt service routine to handle whenever the analog to digital converter is finished. Once it is finished, whether you've checked and you found out that the go bit has now gone back low, or you've got an interrupt, then you're going to want to read the result in ADRESL and ADRESH and go ahead and process the incoming data and do whatever you're going to do with it, whether that be writing out to a display or turning on some other device as a result of the analog quantity. There is some sample code also posted on Blackboard. I'll have a separate video that will walk through that code for you. In this particular code, you are going to be using analog input on AN0, which happens to be the same pin as port A bit 0, and it will use the lower 8 bits to determine a value that will be displayed on a 7-segment display. You'll notice if you compile and run this code that it actually cycles through 4 different times, 0 through 255. And you might think to yourself, why? So I'll leave you thinking about that. Make sure if you do try to run this code on your trainer kit that you turn on the switches that are just below the potentiometers on the bottom left side, just a little bit to the right and above the keypad that we've been using. All right.